this is FRQ Practice 1. So for part A, I'm going to use conservation of energy by starting PE is equal to KE, or PI equals KEF plus PEF. And then the mass is going to be the big mass of the height equals to 1/2 mv squared plus mgh. And then the masses cancel out. And then the h is going to be 3, like initially. And then I'm going to subtract the gh from here to their side. And I know, oh, that's hi and that's hf. And hf is going to be L minus L sine of 25. So I'm going to take out the L, which is 3, outside. And then that's going to be 1 minus sine of 25 degrees equals to 1/2 v squared. Then after simplifying everything, you're going to get v, the instantaneous speed at 25 degrees is 4.98 meters per second. For part B, I'm going to find the angle that we need to use for it. So I know this is FG, this is FG, I'm just going to label that FG, that's FGY, and that's FGX. And you're not going to use this angle right here, no, because you need to use this angle. That's because I think I can show that right here. So this is going to be the alternate interior angle, and if this is 25, then this has to be 65. Wait, hold on, how do I, yeah. So if that's 25, then, oh wait, oh yeah, this angle right here, 90 is going to be 90 subtract 25, which is going to be 65. And then this is going to be that, because I forgot one of the names, but I just know I have to use this angle. And then the net acceleration is going to be so first, I know a total, I have to do rad AC squared plus a tan squared. And now I'm just going to find each of the parts. So AC is V squared over R, and we're going to use the V from the previous problem, or from the previous answer I got, which was 4.98 squared over radius, or which is the length of the string, is 3. And you're going to get about 8.28 meters per second squared for the centripetal. And then for A10, I can do FGX equals to MA, and then FGX is mg sine. Yeah, mg sine of 65 equals MA, and then cancel. So that's A10. A10 is going to be g sine 65, which is going to be 8.88. And now a total, or net acceleration, is going to be, I put everything in. So then a total is going to be 12.14 meters per second square. And you asked for the magnitude, so yeah. Then part C. For part C, it asks for the angular acceleration when it is 25 degrees below the release point. So for angular acceleration, I know I need to use A10, because that's like at the end of the, or at the end of the string, and that's like making it rotate. So A10 is going to be R, or you can put L times alpha. And then I'm going to use the point, or A10 from the last question I got, which was 8.88. And then length is 3, and angular acceleration is that's alpha. Not angular acceleration, yeah, angular acceleration. Yep, and then 8.8 divided by 3. So angular acceleration when it's 25 degrees below the release point is going to be 2.96 rad per second square. 2.96 rad per second square. Okay, so for part D, it asks for the tension in the corner at the lowest point of the spring just before it strikes the block. So in order to do that, I know I need to find V when it reaches the lowest point, so then I can find T, because finding V will give me FC, and after that I can find T. Excuse me. So first I'm going to use conservation of energy to find the final velocity equals KEF, and mgh equals 1/2 mv squared. So VF at lowest point is going to be 2gh rad 2gh, yes. So then you just plug everything in. So then, oh, that's HI, yes, HI, okay. The final velocity at the lowest point is 7.67. And then from there, I know FC equals to mv squared over R. So then, I'm going to plug in the mass. Oop, it's a big M, not small m. mv squared over R. And then, that's going to be 1.8 times 7.67 squared over 3. And then, oh wait, I think I need to use write the whole general equation. Hold on. So, at FC, when at the lowest point, the string is like that, right? So there's tension, and there's FG. So I'm going to do tension minus FG. If I get tension, I do FC plus FG equals T. So then I just put everything in. I'll have to write this a bit smaller. Okay, 1.8 times 7.67 squared over 3 plus, and then FG is just mg, 1.8, that's m, and then g is 9.8 equals to t. Yes. So tension, after you put in a calculator, you're going to get tension is equal to 52.92 Newton. Yes. Oh, I should have wrote the general formula for this. But this is the general formula. Yep. Okay. Next one, part E. Oh, it's going to be a lot of algebra. So first, I have to use conservation of momentum. And I know initially, the only thing that was moving was the ball. So it's MVI, I'm going to call this 1, equals to MVF of 1. And then plus the block is going to have a final velocity as well, MVF 2. And then I know I can also use kinetic energy, because this is a conservation of kinetic energy, because this is an elastic problem. It's perfectly elastic. So I'm going to do MVI squared equals to MVF squared 1 plus MVF2 squared. So then I'm going to isolate for VF2 because I'm trying to find VF1. So MVI1 minus MVF1 equals to MVF2, MVI1 squared minus MVF1 squared equals MVF2 squared. And then I think it'd be easier if just put all the numbers instead of keeping the variables. So 1.8, which is the mass of the big one. Velocity I'm going to use for initial is the one when it's at the lowest point, which was 7.67. And then subtract 1.8, and this one you don't know. And then this is 0.4, VF2. Now I'm going to divide everything by 0.4. So then VF2 is going to equal 34.51, subtract 4.5 VF1. Yes. And now I'm also going to plug in all the numbers for the kinetic one. So this one is going to be 1.8. It's going to be the same thing as the momentum one, but has a square after the VF. Okay, and then I'm going to simplify that into, yes, this is going to be 105.84 minus 1.8 VF1 squared equals 0.4 VF2 squared. Okay, and now I'm going to square both sides of this so I can substitute VF2 squared into this equation. Okay. So after you square it, you're going to get VF2 squared is going to be 1190.7 minus 3110.56 VF1 plus 20.25 VF2 squared. And now I'm going to put this in there. Yes. So then 105.84 minus 1.8 VF1 squared equals 0.4. And 1190.7 minus 31 VF1 plus 20.25 VF1. F2. Okay. F2 squared. And then you distribute after distributing. Oh, it's going to be more. Okay, we can do this. 105.84 minus 1.8 VF1 squared. And after you distribute, you get 476.28 minus 124.22 VF1 plus 8.1 VF1 squared. Oh, did I accidentally write that too? Oh no, that's supposed to be VF1. Okay, and then you combine like terms too. So I'm going to get the quadratic equation as 9.9 VF squared minus 124.22 VF plus 370.44 equals 0. And then you put them in your calculator, and you're going to get VF1 is equal to positive 4.88 meters per second. Oh, that was a lot of work. Okay, next one, the velocity of steel ball meter after, F. We just did E. Okay, for F, I know after like it get hit by the ball, it's going to go through the tough surface, and the only force going to be acting on that in that time is going to be the force of friction. So I know Fk is going to be the only force there, so it's going to be, so net force is going to be Fk, which is equal to Ma. Or net force is equal to Ma, and then that's going to be equal to friction, because that's the only force acting on it. So I know Fk is mu k times Fn. So then I'm going to do, and then mu k is mg, of the smaller mass, equals to Fk. So then I'm going to put that back into Ma equals mu k mg. And the masses cancel out, so A is going to be mu k g. A is equal to, mu k is 0.16 g. So A is going to be negative 1.568 meters per second square. And then after I find acceleration, I can use that to find the final velocity. Oh, wait. Yeah. So after I find acceleration, I'm going to find the final velocity of the block after the collision. So to do that, I just plug back what I know for the final velocity I got for the sphere back into the moment of conservation of momentum. So I'm going to copy and paste this general. Oh, wait. I'm just going to copy and paste this general formula. And then put it back here. And then I'm going to do mvi1 subtract mvf1 equals to mvf2. And then I know it's 1.8, 7.67, subtract, use the answer of vf1 I got from the last one is 4.88 equals to 0.4 vf2. And vf2, the block, is going to be 12.55. And after that, I'm going to use vf equals to at plus vi. And then ask for when it comes to rest, so it's vf is 0. And negative vi, negative vi, which is going to be the vf2, because the vi is the velocity after the collision. So after the collision is 12.55, and for it to come to a stop, that's what we're trying to find a time for. Yeah, does that make sense? But yes, we're going to use 12.55. And then acceleration was negative 1.568 to get t, and t is going to be 8 seconds. For part G, I'm going to use common form to find the distance, and then after that, I'm going to find 3/4 of the distance. So G, vf squared minus 12.55 squared. Hold on, I read it. General formula first. Okay, so to find the final velocity after it travels, no. Oh, this is for first when it comes to stop, yes. And then initial is going to be 12.55 square. And then to get the distance, I'm going to divide by 2a. So a was negative 1.568. So then distance is going to be 50.18. 3/4 of that distance is 37.64. And then again, I'm going to use common form to find the VF2 before it hits the block, before it hits the rod. Yes. So then VF square, I'm just going to add VI square to the side, 280 plus VI square. And then VF square is going to be 2, negative 1.568, 37.64, which is the distance we got before. And then plus 12.55 square for the initial velocity. And then VF2 is going to be 6.27. And then after that, finding that final velocity, which is going to be the initial velocity, final velocity after it travels that distance, and that velocity is going to be the initial velocity before the block hits the rod. So I know I can use angular momentum. And then I'm going to set up this general formula, mvr equals I total wf. And I'm just going to find I total first, which I think will help. I total is going to be 1/3 ml squared plus ml squared. And then I just plug in what I know. So 1/3 times 1.1 times 5 squared plus 0.4. And it was 2/3 length. It's going to hit the rod at 2/3 length from its end. So then I total is going to be about 13.61. And then after that, I know I can plug in everything I know. So I'm going to do, this is VF2. Yes, so then, I think I'll just write down here. Okay, 0.4 times VF2, which has got the final velocity after it travels that 37.64 distance. So then 0.4 times 6.27, 2/3 5 equals to I total, which I got was 13.61, and WF. So then if you divide 13.61, the final angular speed immediately after the collision is going to be 0.61 rad per second. Okay, part H. How high would a rod block system rise after collision? I know I can use conservation of energy again. So the only kinetic energy for this one is going to be rotational because it's moving rotational. So 1/2 IW squared equals to M plus M GH. And then this is going to be I total again. So then I'm just going to plug in the final angular speed I got from the last problem. And yeah. And also the I total, which is 13.61. 0.61 squared equals to 1.1 plus 0.4 GH. And then after you simplify, you get 0.598 equals to 1.5 GH. So then the maximum, or how high the rod block system will rise after the collision is 0.17 meter. Okay, so for part I just write up here. I know Li is going to be LF, and Li for this system is going to be MVR. So initially, the length was 2/3 L. And then when you change it to L over 2, let's say both of these, this is going to become 4 over 6L, it's going to be 3 over 6L. And when you look at it, this has a lower moment of arm, and since it's lowered, it's going to decrease Li, or initial angular momentum. And when that decreases initial angular momentum, the final angular momentum will also decrease. And when final angular momentum decreases, the I total and WF, both of these will decrease as well. Why? Because I total, it depends on, 1/3 ml squared, it doesn't change, but the ml squared, it does change, because before it was higher, so which means to make I total bigger, but now that the moment of arm, which is this, decreases, it's going to decrease the I total as well. And not only does I total decrease, WF will decrease as well, because the final angular momentum decreases, the final angular speed has to decrease as well. So then, and I total will also decrease because 1/3 ml squared plus ml squared, and this L is going to be like into there. So when this is less, the I total is also going to be less. So both of these are less, which is why final angular momentum will also be less. And this is all because initial angular momentum is less because of MVR, which decreases because of L over 2. Yes, thank you.